So another application of differential equations and integration is using logistical growth models or logistics growth models. Um, Unrelated to Euler's method, but let's go out to the side and let's think back about what we know about an exponential growth model. So I know that if I have a differential equation in the form, I'm going to say dy dt equals ky, where k is a constant. In fact, we sometimes call this the constant of proportionality, or we could think of this as the growth rate. That when we integrate this, so if I were to go through the steps to separate and integrate here, we would get an equation in the form of y equals c times e to the kt. And again, like, I don't know what c is unless I have a particular initial condition, but we could solve this as a differential equation. So if we look at a quick example of, let's look at an example of an exponential population growth model. So we could say that dp dt, the rate of change of population with respect to time, is equal to, let's say that our population is growing by 5%. So that would be 0.05 times p, our population. And so we could think of this as being proportional. So what that means is that the rate of change of the population is proportional to the population itself. And when we go back to proportional relationships, we learned those in the beginning, probably like 7th grade math. That's when I am basically multiplying by some constant of proportionality. So in like middle school math, when you learn about proportional relationships, it's almost like I'm graphing y equals mx and b equals 0, if I kind of take that back to middle grades math. So if we were to integrate this, and we have hopefully done this a little bit in Algebra 2, if I wanted to solve and find a particular solution, or in this case, we'll just find a general solution for our population model here, we could first separate our variables. So notice that there is no variable t, but there is a variable p. So I would still multiply both sides by dt. So we would still get like dp equals 0.05 p times dt. And then I know that I would at least need to get my p to the other side, my p variable. So that's like 1 over p, or I could write that as dp divided by p equals 0.05 dt. I'm going to leave the 0.05 on the right. So I notice that there's no t input. That's okay though. We have separated. We are now going to integrate. So when we integrate this, we know on the left we're going to get the natural log of the absolute value of p. And on the right, we're going to get 0.05 t plus some constant c, so our constant of integration. So as we go to solve this, when we exponentiate both sides here, I'm going to get the absolute value of p equals, and remember, using my exponent properties, I could think of this as e to the c times e to the 0.05t, which is the same as c e to the 0.05t. And because we haven't actually found c yet, we could drop our absolute value here because we don't know if our unknown constant is positive or negative. And we would find out if we ever plugged in an initial condition. So this is an example of a population growth model that is exponential. And this particular model, this is like unbounded. It is unconstrained. If I think about an exponential curve, I know an exponential curve is going to get really, oops, wow, that was weird. Well, that looks like a heart. I don't know what just happened. An exponential curve is going to go up and get really, really steep. And we know to the left would have this asymptotic behavior. So we don't know constant of integration, but we know an exponential model as t approaches infinity is just going to blow up. And we know that in Algebra 2, for example, when we work with things that we can model exponentially, we might have this equation, sometimes we call it a part, where we have our initial like input, we could think of that as like a principal times e to the RT, which is rate times time. So again, this model will always give us something that looks like this, and our original differential equation was really in the form of some constant of proportionality times y or times p, whatever our dependent variable is there. So in real life, we often have constraints. There might be some type of constraint on our growth. And so when we think about population growth, a constraint on the growth might be something like resource scarcity. And just for like a small example, let's say that there's, I don't know, let's think about the Galapagos Islands. We know that they have all types of endemic animals there. There might be some form of, I don't know, like turtle that lives there. And even if the population were to grow initially at an exponential rate, at some point you run out of physical space for that many turtles, right? Or you run out of food sources for that many turtles to survive. So resource scarcity will also impact population growth. So a logistical model or logistics growth model will take that into account. All right, so when we see a logistics model, this might look a little confusing at first, but the good news is we don't have to know too many things about this. We really have to understand what the model is. So in a logistics growth model, we're going to see our differential equation in the form of like dy dx equals ky. So that first part, that looks like our constant of proportionality times y. That looks just like our exponential model. But then this gets multiplied by this factor of 1 minus y divided by a. And in this model, we're going to think of k as our growth constant. So that's like our growth factor or our growth constant there. And a is the carrying capacity. So we could think of the carrying capacity as really like that. I could think of that as like the maximum, like where my growth or where my population has to top out. So if we were to find this solution, and we're not really going to need to do this, so if we could just kind of follow along with this example, if we were to find this solution, the thing that I want to point out that's really important is that what we're going to do with this, we really need this number to be 1. So if that's ever not a 1, we're going to need to factor something out so that we can actually determine what our carrying capacity is and what our growth constant is. But if we just kind of follow the steps to how we can derive this formula, if this is our dy dx, we know that we would, to solve a differential equation, the first thing we would do is separate our variables. And again, like the only variable here is y. We don't actually have an x in our equation, but that's our other variable. K is a constant, and a, the carrying capacity, is also a constant. So we would separate our variables, and then we would integrate. And we're not going to go through this now, but to do this, we would need to use partial fraction decomposition. We're going to come back to that later in the course. But when we integrate, we would end up with this antiderivative, and we would remember our plus c, and then we could use some log properties here to combine this left-hand side of our equation, that a difference of logs becomes a log of a quotient. And then we would isolate y, so we would exponentiate both sides here to get to this next step where y is not yet isolated, but we've gotten rid of the logarithm. And then we would multiply by y minus a on both sides. And then we could take a few more steps here where we could like distribute that. And we could use some just algebraic properties here. We could factor because we're trying to isolate y. And we end up getting this equation that if we were to then get like not a common denominator, excuse me. If we were to like simple this up a little bit to get rid of the c times e to the kx in our numerator, we could just get a in our numerator. We're going to multiply by this version of 1 right here to simplify up our numerator, and this is what we get as our equation. So this particular equation, y, is a solution to this differential equation dy dx. And AP is not going to ask us, AP is not going to ask us to do this. Like, we're not going to actually have to solve a differential equation like this, but we want to be able to recognize the form here. The other thing that we want to know is what a logistics model looks like. So graphically, we said an exponential model is unbounded and it goes on forever. But for a logistics model, we said that there is a carrying capacity. So as our graph, I'm going to do the logistics model over this one. So as our graph gets closer to our carrying capacity, we're going to have this asymptote here that represents our carrying capacity. What our model is going to look like is it's going to grow fast, but then it's going to slow down as it approaches that capacity. So our logistics growth model is going to have asymptotic behavior on both the left and the right, unlike an exponential growth model that is unbounded. So that's another thing we really need to know about logistics growth models is we need to know what the graph looks like. We need to know that there's going to be a horizontal asymptote at the carrying capacity and also on the x-axis, so where y equals 0. So we said our main ideas that we need to understand about logistics growth models so far is we want to recognize when we see their differential equation, again in this form, we might have to pick out a constant if that 1 is not in fact just a 1, or factor out a constant I should say. We said we need to know what their graph looks like, and we need to understand that k is our growth constant. So again, it's important that k is our growth constant and that a is our carrying capacity. We could look at this box that if we were ever to actually integrate and find a solution to this differential equation, that it would be in this form here. So this might be important for us to kind of recognize this form, where again, a is the carrying capacity and our constant of integration, well, or what becomes our c value rather, is equal to like y naught divided by y naught minus a. All right, so let's, on this next page, we have a slope field at the top of page 72, and this is a slope field for this particular differential equation. Dy dx is 0.05y times 1 minus y over 10. And so I need to be able to recognize this like form of dy dx and recognize that this is a logistics growth model. We are given that our initial y value is 2. And so we could find our c value there, 2 divided by 2 minus a. So 2 over 2 minus 10, we get negative 1/4. We are given that our growth, like our growth factor is, our growth constant is 0.05, and that a, our carrying capacity, is 10. So these are all things that we should be able to identify from this differential equation. So when we go to write that as the curve, and again we can use what we have in our box above, that when we write our solution for y, we get this. And this curve is shown on the slope field. So this is the red curve on the slope field to the right. And so what we want to notice, and I'm going to zoom in on the slope field. So in the slope field, our carrying capacity, we said that that happens at 10, meaning that this population this population can't really grow beyond 10 or can't be sustained beyond 10. So this asymptote right here, this is at our carrying capacity, which we said is A. And we'll also notice that we have an asymptote, a horizontal asymptote down here at 0. So if we look at a particular solution, a solution curve to this differential equation, we have a solution here that goes through 0, 2. So like as I trace that curve, I notice it's going to go fast, but it's going to slow down as it reaches the asymptote, so as it reaches the carrying capacity. And to the left, it looks a little bit more like an exponential curve looks like on the left. We have an asymptote on the left. So I can tell that if I start, if I pick an initial point that is between 0 and my carrying capacity, if that's one of my initial points, that I'm going to see this logistics curve here. And I'm going to notice that the limit of this curve, so the limit of y as x approaches positive infinity, is going to be our carrying capacity. So in this particular case, our limit is going to be 10, because that population isn't going to be, like, we're not going to have sustained growth beyond that capacity. If we were to instead start somewhere above, like if we started at a population that is above the carrying capacity, we could see that that population is going to have to decline until it also approaches A. So we could see that solution in our slope field if our initial, like if the population we're working with is above the capacity. And I couldn't think of any examples in context where a negative value would make sense. Like we literally can't have a negative population, but just to get an idea of what the slope field looks like beneath it, that if we started it in the negatives, the slope field would go down, down, down. So it looks like towards negative infinity as x approaches infinity. I don't think that part of our slope field is as important. So putting this together, we could see that if we consider as x approaches positive infinity, our solution is going to approach our carrying capacity, going towards negative infinity. And again, this is when I'm choosing a point on the curve that is between 0 and the carrying capacity, then my limit will approach 0. One other thing we might want to consider about this model is when the population can achieve its maximum rate of growth. So in a logistics growth model, we said that our function does grow exponentially up until a certain point, but then the growth rate slows as our function approaches its carrying capacity. And it is useful to know when this happens. So again, if I think about what this graph looks like out to the left, like if this is my carrying capacity, my function's exponential, but then it slows down. So really what we're looking for is where could we maximize our growth? And looking at this graph, I could think about this as like, when is the slope of my curve or the slope of my tangent line to this curve, when is it the steepest? That's kind of what we're looking for there. So what I'm thinking of really is if the curve is represented by dy dx, I'm thinking about when dy dx is at its maximum or its greatest value. Because if this is my curve, that's when my tangent line would be the steepest. So I was approximating on this curve I drew. It looks like it's about there. Maybe that's not the best approximation, but that's not the best curve. All right, so if I wanted to maximize dy dx, so again, if we look at dy dx, we said for a logistics model, this is in the form of ky times 1 minus y divided by a. The first thing we would need to do to maximize anything is to find its critical values. So we would take our derivative of dy dx and set it equal to 0. So our derivative of dy dx is our second derivative, d squared y over dx squared. So just using the product rule here, And again, I don't think we need to write this out from scratch. We could just kind of follow along with this example. Using the product rule, I would get k times y prime, so that's the derivative of my first factor, times my second factor, 1 minus y over a, plus the derivative of 1 minus y over a. Remember, a is a constant, so we don't need the quotient rule there. The derivative is just 0 minus 1 over a times y prime. And I would multiply that with my original factor, ky, my first factor, ky. So if I just kind of follow through this example, we can distribute ky prime to those first two terms. We could, well, there's nothing to distribute here in our next two terms. We just kind of wrote that a little bit differently. So then we could combine any like terms, and then we could factor out our ky prime. And that is our second derivative there. Like, that is simplified for our second derivative there. So again, if I'm finding critical values, I'm finding critical values of dy dx. That's going to occur when the derivative of dy dx is equal to 0. So when I set this equal to 0, I know k times y prime is going to be 0. That is like one of my factors. But what I'm really looking for is what y values are going to make this 0. So if I set this factor, 1 minus 2y over a equal to 0, I could just add 2y over a to both sides. I get 2y over a equals 1. And I could rewrite this by multiplying both sides by a over 2 to get that y equals a over 2. So here's what we really need to know from that. We need to know that our maximum growth, the maximum rate of growth in a logistics growth model, will always occur when the population is at 1/2 of its carrying capacity. So again, y, our population here, is equal to 1/2 times the carrying capacity. And we don't actually need to take that derivative again. That fact is always going to be true. So if we look at our solution curve above, like the actual slope fields, not the terrible one I drew out to the side, when we are halfway to our carrying capacity, this is the spot on our curve that's going to be where our slope of our curve hits its maximum. I might also notice that that is a point of inflection of the curve, that the curve to the left is concave up and to the right is concave down. So again, this happens when we are halfway. So this is happening here where a is equal to 5. So it's the population when our a value is 5, our carrying capacity is 5. Well, our carrying capacity is always 10, but 5 is 1/2 of our carrying capacity is what I meant to say. All right, so if we look at these last two examples, that's a lot of information. When we actually work through these, if we can synthesize that information, the math itself isn't very difficult. We just have to be able to recognize that we're working with a logistics function. So in this first example, a population can be modeled by a logistics function P of t satisfying the differential equation dp dt equals p over 3 times 300 minus p. And recall that we are looking for this to be in the form of like dp dt, or dy dt is how we wrote this earlier in the text, is like k times y times 1 minus y over a. And remember, we said that if this number is not a 1, we're going to need to do something here. So this number right here is not a 1. That's a 300. But in order to make it a 1, I could factor out a factor of 300. So dp dt is equal to p over 3. I'm going to pull out the 300. And now in parentheses, I'm left with 1 minus p divided by 300 because I have to factor that from both terms. So if I simplify this, that's like 300p divided by 3. That's really just 100p times 1 minus p divided by 300. All right, so this is our dp dt. in a form where we could figure out our carrying capacity. So A, our carrying capacity is 300, and we could tell what our constant growth rate is. K is equal to 100. So our first question, if P of 0 equals 100, we are asked to evaluate the limit of P as T approaches infinity. So P of 0 equals 100. 100 is between like 0 and our carrying capacity of 300. So again, if I think about that curve, if here's my asymptote, if I pick a value to start at that's between 0 and my carrying capacity of 300, I know that to the right, I'm going to approach that asymptote, and to the left, I'm going to approach 0. So for question A, as t approaches positive infinity, we're looking to the right of the graph. The answer to this is just 300. Now, if I choose P of 0 is 500, so if I think about if my initial output is above my carrying capacity, but I'm still asked to evaluate the limit of P as t approaches positive infinity, if I start above my capacity, I'm just going to come down towards that asymptote. So for the second example, our answer is still just 300. That is just our carrying capacity there. And then in part C, at what population is the growth rate of the population at its maximum? And we said that this occurs when our population is 1/2 of our carrying capacity. So since our carrying capacity is 300, our population is 150. So we could say that at a population of 150, our growth rate is at a maximum. All right, this very last example, if you want to try it on your own, I would say don't forget we need to factor. All right, a population is growing at this rate, dp dt. We're given an initial population of 100, so P of 0 equals 100. So I would first factor out a GCF, and I would take a P with it, right? So if we rewrite this in factored form, I have 1/100th P, and what I'm left with in parentheses, and remember this decimal, when I divide this by 1/100th, that's just going to move my decimal 2 places to the right. All right, so this is dp dt in our factored form. And I know it's probably easier to work with this as a fraction, or at least what's in parentheses as a fraction. So this is 1/100th P times 1 minus, well, that is 1 in the 1,000th place. So that is P over 1,000 there. So we are asked, what is the carrying capacity? Well, the carrying capacity is 1,000. We are asked to evaluate the limit of P as t approaches negative infinity. And remember, we're starting with this initial P value of 100, which is between 0 and our carrying capacity. So again, as we go to the left, we're going to have that asymptotic behavior that our function P is going to approach 0. Because again, we said to the left, this looks like our exponential curve. And it starts exponential to the right, but then it dies off at the carrying capacity. I'm not sure dies off is mathematically accurate, but you know what I mean. And then finally, at what value P does the population attain its maximum rate of growth? So if our capacity is 1,000, which we had to manipulate this to see, this is going to happen when y equals 1/2 of 1,000, which is 500. So when our population is 500.